Hello. I wish you doing well. Today we'll all talk about black hole. A black hole is a region present in space-time, space with its 4 dimensions, which is the 3 dimensions in addition to time, characterized by a very strong gravity so that nothing, not even particles or electromagnetic radiation waves like light, can escape from them. General relativity predicts that a compressed mass of a certain amount can distort space-time to form a black hole. The boundaries of an inescapable area are called the event horizon. Although crossing the boundaries of the event horizon has enormous effects on the fate and conditions of any object that crosses it, no observable properties appear to this region. 4. The black hole acts as an ideal black body, because it does not reflect any light. Furthermore, the quantum field theory of curved spacetime predicts Hawking radiation emission of event horizons, with the same spectrum as that of the black body to a temperature inversely proportional to its mass. This temperature is at the limits of a billionth of a Kelvin of black holes from the stellar mass, which means that it cannot be observed. Jean Michel and Pierre-Simon Laplace both indicated that there were bodies with strong gravitational fields that light could not escape from in the 18th century. Karl Schwarzschild found the first modern mathematical solution to the general relativity characterizing the black hole in 1916, but the interpretation of the mathematical solution formed the space from which nothing could have escaped, first published by David Finkelstein in 1958. It was black holes are a fantasy and curiosity of mathematicians for a long time. But during the 1960s, theoretical work showed the general relativity prediction of holes. The discovery of neutron stars by Jocelyn Bell Bornell in 1967 sparked interest in compact objects that collapsed with gravity as a possible astrophysical reality. It is believed that black holes with stellar mass form when very massive stars collapse at the end of their life cycle. After the black hole forms, it can continue to grow by absorbing the mass from its surroundings. This is done by absorbing other stars and merging with other black holes, which may lead to the formation of massive black holes that carry a mass equivalent to millions of solar masses, m. There is general consensus that there are massive black holes in the centers of most galaxies. Although its content is invisible, the presence of a black hole can be inferred by its effect on other substances and electromagnetic radiation such as visible light. The material that falls into the black hole can form an external accumulation disk that is heated by friction, forming some of the brightest objects in the universe. If there are other stars orbiting a black hole, then both their orbits and mass can be used to determine the mass and location of the black hole. These observations can be used to exclude potential alternatives such as neutron stars. In this way, astronomers have investigated many cases of predictions of the existence of an astral black hole within binary systems, and have proven that the radio source known as the Irami name, at the heart of the Milky Way, contains a massive black hole that has a mass of approximately 4.3 million solar masses. On February 11, 2016, the LEGO Observatory Alliance announced the first direct discovery of gravitational waves, which reflect the idea of finding the moment when black holes merged. As of December 2018, 11 gravitational waves have emerged from the merger of 10 black holes, and 1 gravitational wave resulting from the fusion of a binary neutron star. On April 10, 2019, the first ever image of a black hole and its surroundings was published, following readings obtained by the telescope of the Event Horizon in 2017 related to the massive black hole in the center of the galaxy Messier 87. In a research published in November 1784. The English astronomer and English cleric Jean Michel proposed his conception of the existence of a body so large that it would not allow light to escape from it, and it was concluded that such an object would form when a star's diameter exceeds the diameter of the Sun by 500 times. It calculates that the escape velocity of its surface will exceed the usual speed of light. Michel pointed out that these super-invisible but invisible objects can be discovered through their gravitational effects on nearby visible objects. The researchers at the time were enthusiastic about the suggestion that there were giant but invisible stars in front of them, but that enthusiasm diminished when the wave nature of light became known in the early 19th century. The proposition then became that light is a wave and not a particle. Therefore, The effect of gravity on waves will not be measured by the same method of measurement used on particles, that is, if there is an effect of gravity on light waves. Modern relativity mistook Michel's view of the possibility of a ray of light, rising from the surface of a huge star, begins to slow due to the star's gravity, then stops, and then falls back onto the surface of the star as if it were a ball. In 1915, Albert Einstein developed his general theory of relativity, as he had previously demonstrated that gravity affected the movement of light. Just a few months later, Karl Schwarzschild found a solution to Einstein's equations of field, which described the gravitational field of both the point mass and the spherical mass. A few months after Schwarzschild's results, Johannes Drust, a student of Hendrik Lorentz, presented the same solution, independently of Schwarzschild's work, to describe the point of mass, and wrote in depth in a better and broader detail of its properties. Within the results and solutions of Johannes, a result emerged, known today as the Schwarzschild radius, where the point translates to a singular position, which means that some of the variables within Einstein's equations have become infinite. The nature of this was not fully understood at the time. In 1924, Arthur Eddington demonstrated that uniqueness disappears after changing coordinates, say Eddington-Finkelstein coordinates, but it took until 1933 until George Lemaitre realized that this meant that uniqueness in a radius of Schwarzschild amount was a uniqueness in non-physical coordinates. Arthur Eddington wrote, commenting on the possibility of a star with a compressed mass of the size of Schwarzschild's radius in a book published in 1926, stating that Einstein's theory allows us to exclude very high densities with invisible stars such as the headstock of Gemini because a star with a diameter of 250 million kilometers cannot have a density as high as that of the Sun. First, the force of gravity will be so great that light will not be able to escape from it, and rays will fall to it again as the stone falls back to Earth. Second, the redshift will be so great that the spectrum will shift out of existence. Third, the mass will produce a great curvature in the scale of time and space, so that the space around the star is closed, leaving us outside, that is, anywhere. In 1931, Subrahmanyan Chandrasekhar, using special relativity, concluded that an object not orbiting and made up of electron-dissolved matter and a mass above a specified value, now called the Chandrasekhar limit of 1.4 m, would not have stable solutions within relativity. His conclusions were opposed by many of his contemporaries such as Eddington and Lev Landau, who replied to him that there must be unknown mechanisms that would halt the collapse of the material. Their opponents bar some validity. The white dwarf slightly larger than the Chandrasekhar limit collapsed into a neutron star, which is a stable body in itself. But in 1939, Robert Oppenheimer and others predicted that neutron stars above another boundary, Tauman-Oppenheimer-Volkov limit, would collapse based on Chandrasekhar's explanations, and concluded that there was unlikely to be any physical law that could halt the collapse of some stars, which meant turn it into black holes. Their original calculations, based on the Pauli exclusion principle, set the value of the new boundary to 0.7 m. The subsequent understanding of the high force affecting the repulsion of neutron stars raised the estimate to values ranging from 1.5 m to 3.0 m. 27. The readings recorded at the LEGO Observatory of the gravitational wave resulting from the merger of the neutron star GW170817, which is believed to have led to the appearance of a black hole shortly thereafter, improved the estimate of the Tauman-Oppenheimer-Volkov limit to 2.17 m. Oppenheimer and his colleagues interpreted the uniqueness on the boundaries of the Schwarzschild value radius as an indication that these are the boundaries of the bubble within which time stops. An appropriate viewpoint for observers outside the bubble. But it is certainly not what the object falling inside the bubble observes. Because of this characteristic, collapsed stars were called frozen stars, because the outer observer will see the star's surface frozen in the moment that the collapse's size reaches the Schwarzschild radius. In 1958, David Finkelstein admitted that Schwarzschild's surface is an event horizon, an ideally unidirectional membrane. Causal influences can cross it but in only one direction. This was not in stark contrast to Oppenheimer's results, but expanded its notions to include the viewpoint of objects that transcended the event horizon. Finkelstein's solution allowed Schwarzschild's solution to bind to the future of objects that fell into a black hole. Martin Kruskal was able to find a complete solution and quickly deploy it. These results came at the beginning of the golden age of general relativity, which was characterized by the prevalence of issues of general relativity and black holes as major topics of scientific research. This was aided by the discovery of pulsars by Jocelyn Bell Bornell in 1967, which, by 1969, had been shown to be neutron stars orbiting at very high speeds. 38. Until that time, neutron stars, like black holes, were viewed as mere flanks and theoretical intellectual luxury. However, the discovery of pulsars demonstrated their physical importance and sparked additional interest in all types of bodies collapsed by gravity. In this period, more general mathematical solutions to black holes were found. In 1963, Roy Kerr found the exact solution to the rotating black hole issue. 2 years later, Ezra T. Newman found the mathematical solution to simulating a symmetric black axle rotating and electrically charged. Through the work of Werner Israel, Brandon Carter, and David Robinson, no-hair theorem emerged, which states that a fixed black hole can be fully described by three characteristics: Kerr-Newman measurements only, mass, angular momentum, and electric charge. Initially, it was believed that strange features appearing in mathematical solutions to black hole models were extreme results due to the assumption of the condition of symmetry within mathematical models, and therefore these individual results should not appear in mathematical solutions that explain general models. This opinion was espoused in particular by Vladimir Belinsky, Isaac Kladnikov, and Evgeny Lifshitz, who attempted to demonstrate the absence of exclusivity in public mathematical solutions. However, Roger Penrose and Stephen Hawking, in the late 1960s, demonstrated that individual characteristics actually appeared in general mathematical solutions. The work of James Barden, Jacob Bekenstein, Carter and Hawking in the early 1970s led to the formulation of the laws of thermodynamics for the black hole. These laws describe the behavior of a black hole consistent with the laws of thermodynamics by linking mass with energy, space with entropy, and surface gravity with temperature. The idea was integrated when Hawking, in 1974, concluded that quantum field theory predicts that black holes should radiate the same as the black body at a temperature proportional to the surface gravity of a black hole. John Michell used the term dark star, 49, and in the early 20th century physicists used the term collapsed gravitational body. Science writer Marshall Bertosiak has traced the term black hole to physicist Robert H. Mitchell. Dickey, who is said to have compared this phenomenon in the early 1960s with a black hole in Calcutta, a famous prison that people enter alive and take out from the dead. The term black hole was used in magazines within the magazines of Life and Science News in 1963. And journalist Anne Ewing used it in her article Black Holes in Space, on January 18, 1964, where she wrote a report on a meeting of the American Association for the Advancement of Science in Cleveland, Ohio. One of the students was said during a lecture by John Wheeler in December 1967 that he proposed the phrase black hole. Wheeler adopted the term, and its usage soon spread, which prompted some to give Wheeler credit for formulating the phrase. The hairless theory assumes that, once the black hole reaches a stable state after its formation, it has only three independent physical properties: mass, charge, and angular momentum. Otherwise, the black hole does not have any other properties. If the hypothesis is correct, then this means that it is impossible to distinguish any of the black holes that share the same values for these properties from each other. The degree to which theory corresponds to black holes on the ground, and according to the laws of modern physics, is a problem that has not yet been solved. These characteristics are special because they are visible outside the black hole. For example, a charged black hole would be repulsed with charges that resembled its charge just like any other charged object. Likewise, the total mass of a sphere containing a black hole can be found using the gravitational analog of Gauss's law, the mass of the atom, away from the black hole. Please clarify. Similarly, angular momentum can be measured from a distance using the frame pulled by the gravitational magnetic field. When an object falls into a black hole, information related to its shape or charge is distributed evenly along the horizon of the black hole, and its impact is lost by any outside observer. The horizon behavior in this case can be interpreted as a dissipation system with behavior that closely resembles the behavior of an expandable membrane that has resistance to both friction and electrical conductivity, the membrane model. This differs from other field theories such as electromagnetism, which do not contain any friction or resistance at the microscopic level, because they are reversible within time. And since the black hole ultimately reaches a stable state with only 3 properties, this means that there is no way to avoid losing the information that has reached it. The gravitational fields and electricity in the black hole provide very little information about the bodies that cross inward. Missing information includes every amount that cannot be measured out of the black hole's horizon, including roughly preserved quantum numbers such as the Perrins-Hull number and lepton number. This behavior is so puzzling that it has been called the paradox of black hole information loss. The simplest static black holes are black holes, but do not carry an electrical charge nor have angular momentum. These black holes are often referred to as black Schwarzschild holes in appreciation of Karl Schwarzschild, who discovered this mathematical solution in 1916. 17. According to Birkhoff's theory, this is the only spherical solution. This means that there is no noticeable difference between the gravitational field of this black hole and any other spherical field of the same mass. Thus, the popular notion of black hole absorption of everything is only valid within the circumference of a black hole near its horizon. As far away, the outer gravitational field is identical to that of any other object, having the same mass. There are solutions that describe general black holes. Charged non-rotating black holes are described by the Reissner-Nordstrom scale. In contrast, the Keir scale describes a rotating and non-charged black hole. The well-known solution to the fixed black hole is the Kerr-Newman scale, which describes a black hole with a charge and angular momentum. A hallmark of a black hole is the appearance of the event horizon, the boundary within space-time through which matter and light can only pass inward toward the mass of the black hole. Nothing, not even light, can escape from the event horizon. The use of the term event horizon is used in this manner because, in the event of an event occurring within its boundaries, it is impossible for the information resulting from this event to reach an observer outside those boundaries, making it impossible to identify the occurrence of such an event. As general relativity predicts, the presence of a body with a mass induces a distortion of space-time so that the paths that molecules take towards the mass are deflected. On the event horizon of a black hole, this deformation becomes so strong that no paths lead away from the black hole. For the remote observer, the pulses of watches near the black hole will appear more slowly than hours away from the black hole. As a result of this effect, known as gravitational time dilation, it appears that the object falling into a black hole will slow down as it nears the event horizon, and it will take endless time to reach it. At the same time, all processes on this body slow down, from the point of view of a constant external observer, resulting in any light emitting from the body in a darker and redder, an effect known as a shift towards gravitational red. Ultimately, the falling object fades away so that it can no longer be seen. Typically, this process occurs very quickly when the body is gone and in less than a second. On the other hand, the observer, indestructible, as he crosses the event horizon into the black hole, does not notice any of these traces. According to his own hours, which seem to him to work normally, he will cross the event horizon after a limited period of time without noticing any parameters indicating the presence of uniqueness. In classic general relativity, it is impossible to determine the location of the event horizon based on local observations, due to Einstein's equivalence principle. The shape of the event horizon around the black hole is very close to the spherical. For black holes that do not rotate fixed, the event horizon is completely spherical, while for black holes that rotate, the event horizon is bound by spherical problems. We done now. Waiting for second part. Thanks for watching. Goodbye my friends.